In 1948, Paul Erdős and Ernst Straus wrote down a question so simple it sounds like a homework problem. Can every fraction of the form 4 over n for n bigger than 1 be written as a sum of 3 unit fractions? A unit fraction is a fraction with 1 on top. 1/2, 1/3, 1/17. The kind of fraction the ancient Egyptians used 4,000 years ago. So, for example, 4 over 5. Can we write 4/5 as 1 over a plus 1 over b plus 1 over c for some positive integers a, b, c? Yes. 4/5 equals 1/2 plus 1 over 4 plus 1 over 20. 3 unit fractions. Done. Try another. 4 over 7. We claim 4/7 equals 1/2 plus 1 over 14 plus 1 over 14. Let's check. 1/2 is 7 over 14, plus 1 over 14 plus 1 over 14. Total 9 over 14. Not equal to 4/7, so that decomposition is wrong. Try again. 4/7 equals 1 over 2 plus 1 over 15 plus 1 over 210. Check. 1/2 is 105 over 210. 1 over 15 is 14 over 210. 1 over 210 is 1 over 210. Total 120 over 210, which simplifies to 4/7. Correct. Pause. The Egyptians invented this game. Mathematicians refined it. And Paul Erdős, who knew more about prime numbers than anyone else of his century, asked, does it work for every n? To understand why this matters, we step back 4 millennia. In ancient Egypt, mathematicians wrote fractions in a very specific way. Almost every fraction they wrote was a unit fraction. 1/2, 1/3, 1/5, 1/10. If a scribe needed to express a fraction like 3 over 5, they did not write 3 over 5. They wrote it as a sum of unit fractions. 3 over 5 equals 1 over 2 plus 1 over 10. That is 1/2 plus 1/10. If a scribe needed 2 over 7, they wrote 1 over 4 plus 1 over 28. Every positive rational number less than 1 can be written as a sum of distinct unit fractions. This is called the Egyptian fraction theorem, and Fibonacci proved it in 1202 using a greedy algorithm. Take the biggest unit fraction smaller than or equal to your target. Subtract, repeat. So we already know every fraction can be decomposed. The question is how. How long does the decomposition need to be? Are there short decompositions? Can a specific number of terms always suffice? For 4 over n, Erdős and Straus conjectured, 3 terms is always enough. Never 4, never 5, exactly 3. The simplest possible upper bound, the most elegant possible conjecture, and we cannot prove it. For most values of n, finding the decomposition is straightforward. If n is divisible by 4, write n equals 4 times k. Then 4 over n equals 1 over k, just one unit fraction. We can pad with 2 arbitrary unit fractions that sum to 0. Actually, we just use 1 over k and call the other two 0. But if we want a proper 3-term sum, write 1 over k as 1 over 2k plus 1 over 2k. 3 unit fractions. Done. If n is divisible by 3 but not 4, things are nearly as easy, just slightly more work. If n is divisible by 2, that is, n is even but not divisible by 4, say n equals 2 times m, where m is odd, then 4 over n equals 2 over m. To decompose 2 over m, write it as 1 over m plus 1 over m. But the conjecture wants 3 terms. Easy. 1 over m plus 1 over 2m plus 1 over 2m. For n that is 1 modulo 4, 2 modulo 4, 3 modulo 4. For every residue class, we have explicit constructions. The exception is one specific case, a small set of stubborn residues, where the conjecture has never been verified by direct construction. So the conjecture is, in some sense, almost completely proved. It is a conjecture by edge case. The vast majority of n are easy. The interesting question is what happens at the boundary. The hard cases of Erdős-Straus are exactly the primes p that are 1 modulo a small set of specific residues. Specifically, if n equals 4k plus 1 and n is prime, then the easy methods fail. We need a special construction tailored to that particular n. There is a deep modular pattern. If p is a prime that is 1 mod 24, the easy proofs fail. If p is 1 mod 3 or 1 mod 5, easy proofs fail. The hardest residue classes are p equal to 1 modulo 8, 1 modulo 24, certain residues mod 5 and 7 and 11, and so on. For decades, mathematicians have whittled away at these residue classes. As of today, the conjecture is known to be true for every n up to roughly 10 to the 17th power, verified by computer, and for many infinite families of n. But for general n that lies in a stubborn residue class, there is no known way to produce a 3-term decomposition. The conjecture is, in this sense, a tug of war. Number theorists keep eliminating residue classes by finding explicit identities. The residue classes that remain shrink slowly, but no one has found the master argument that handles them all at once. Paul Erdős was, by any measure, one of the most prolific mathematicians of the 20th century. He published nearly 1,500 papers. He offered cash prizes for problems he could not solve himself. For the Erdős-Straus conjecture, he offered no cash prize. That tells you something. Erdős thought the conjecture was likely true, and probably provable, but he never made it a priority. Compared to his work on Ramsey theory, or the distribution of prime numbers, or combinatorics, the Erdős-Straus conjecture was a side question. This is part of what makes the problem strange. It is elementary, it is concrete. A high school student can understand the statement, and it has resisted for 77 years. The conjecture sits in a peculiar zone of mathematics. It is too easy to be glamorous. It is too hard to be solved by elementary methods. It does not connect deeply to other unsolved problems in the way the Riemann hypothesis does. It is, in a strange way, an orphan, a beautiful question with no major theoretical machinery hanging off it. But every year, papers come out, new residue classes get eliminated. The bound for verified n grows. Slowly, painfully, the problem refuses to die. In the last 2 decades, several mathematicians have made serious dents in the conjecture. Christian Elsholtz and Ernst Tao in 2013 gave the most comprehensive partial results to date. They proved that the conjecture holds for all n up to 10 to the 14th, and that the density of bad n in the integers is asymptotically less than 1 over n to the power 1/2 minus epsilon. In other words, the bad cases are vanishingly rare, even if we cannot prove there are 0 of them. Earlier, in the 1950s and 1960s, work by Schinzel, Mordell, and others established the conjecture for many specific residue classes. Schinzel showed the conjecture true for all n that are not 1 modulo 840. Mordell narrowed the open cases further. The computational record keeps moving. In 2019, the bound was pushed past 10 to the 17th. Modern algorithms exploit modular sievers to skip enormous ranges of n at a time. But all of this is whittling. We know more and more about which n the conjecture is true for. We have made no progress on proving it for all n. The architecture of a general proof remains undiscovered. What we have in 2026 is a beautiful question that is true for every integer anyone has ever tested, and a complete absence of any reason it must be true in general. Why has this resisted so long? 3 reasons. First, unit fraction decompositions are deeply combinatorial. Given a fraction p over q, the number of ways to write it as a sum of k unit fractions is wild. It depends on the divisor structure of q. There is no clean formula. Number theoretic tools that work on additive problems, circle methods, sieve methods, give bounds but not equalities. Second, the conjecture is in a sense a divisibility statement. For n in a hard residue class, we need to find ABC such that 1 over a plus 1 over b plus 1 over c equals 4 over n. Multiplying through, 4 times ABC equals n times BC plus n times AC plus n times AB. We need n to divide ABC in a very specific way. This kind of divisibility condition is generally very hard to solve in closed form. Third, the conjecture lives in number theory but does not connect to the major engines. The Langlands program does not see it. Modular forms do not see it. Elliptic curves do not see it. It is a standalone problem with no leverage from the heavy machinery that solved Fermat's last theorem, or the Poincaré conjecture. Erdős-Straus is in essence a problem of bookkeeping at the boundary of elementary number theory. Bookkeeping is hard. It just looks easy. Farce is esquisely. The Erdős-Straus conjecture, after 77 years, is still standing. It is a reminder that mathematics has no shortage of elementary, accessible, beautiful problems that humans cannot yet solve. There is a temptation to think that all the easy problems are gone, that the only open questions left in mathematics lie behind walls of abstraction so high that no normal human can climb them. Erdős-Straus refutes that. A high school student can understand the question. A research mathematician with 70 years of effort behind them cannot answer it. The list of open problems with this character is long. The Collatz conjecture, 3n plus 1. The twin prime conjecture, infinitely many gaps of 2 between primes. The single Goldbach problem, every even number is a sum of 2 primes. Catalan's constant, which we cannot prove irrational. The Erdős-Straus conjecture, all elementary, all resistant. These problems are, collectively, a measure of what mathematics is. Mathematics is the science of structure. When a question is structured well, like the Riemann hypothesis, which sits at the heart of a vast web of analytic objects, we have tools to attack it. When a question is structured poorly, like Erdős-Straus, which lives at the boundary of bookkeeping, we may simply have no tools at all. So the question Paul Erdős and Ernst Straus wrote down on a piece of paper in 1948 is still open. Every fraction 4 over n is almost certainly a sum of 3 unit fractions. We can verify this for any n you name, we just cannot prove it for all of them. The fractions wait, the proof, if it exists, waits with them,